Alright, so now that we know the velocity, what we want to know really is the pressure distribution, because the pressure distribution is what is going to tell you how much forces is exerted on the air bearing, and in particular how much vertical force is exerted on the air bearing such that it doesn't touch such that the top plate doesn't start to collapse onto the bottom plate and doesn't destroy the lubrication layer. So how do we get to the pressure? So note that the equation, so it's always good to just remember what we've done so far. What we've done so far is that we've used the y and the x momentum equation. Those are the two equations we have used, and we haven't used mass conservation. So so just from sort of the motion that we've had, you need to impose mass conservation. You need to balance your momentum in order to solve the problem. You know that we're going to have to say something about the mass statement, so we're going to have to write mass conservation. Another reason why you can think about mass conservation allowing you to find the pressure is because you're going to squeeze a film of liquid in a small gap, and it's that squeezing, because you're trying to squeeze it, you're going to generate large pressures. So that's why now we have to look at the mass conservation equation, and we'll take directly the form of the mass conservation equation, which we used for lubrication layers, which is dH dt equals to partial Q partial X, where Q is the volumetric flow rate. Now, because we changed the frame of reference, and we are now in the frame of reference moving with the top plate, we know that the problem that we are looking at now is a steady problem, and therefore partial h partial t is going to be equal to 0, and q is not a function of time. So what we get is that partial q partial x is therefore equals to 0. That is what we get from mass conservation. That means that the volumetric flow rate at every single location in x has to be the same. It's sort of a trivial expression for mass conservation here, because we are in a steady state, and therefore we can directly write from mass conservation that our equation for mass conservation tells us that the volumetric flow rate should only be a function of x and should actually be a constant as a function of x. That's our statement of mass conservation. So we've done it, but of course we want to link it to our pressure, and we can link it to our pressure because in order to compute the volumetric flow rate, we need the velocity, which is what we have just done. We've just computed the velocity field here, so we need to compute our volumetric flow rate. And our volumetric flow rate, remember, is always equal to the integral along a surface of this is the element, the volumetric flow rate through surface ds, and if we integrate, then we have the entire volumetric flow rate. Now, our surfaces are cross-sectional surfaces, so they are x equals constant, and that means that our n vector here is going to be the x vector, is going to be the unit vector in the x direction. This here, so u dot n is going to be just equal to the x component of the velocity, so that is u. Our element of surface ds, because we're looking at a cross-sectional surface, so we're looking at a surface which is across the flow, ds is just going to be dy. And then we need to integrate between 0 and the height of the film. So we need to integrate between 0 here and h of x. And so now we just need to compute this integral, and this integral here we can compute because we know what we know here what the dependence on y is. Even though we don't know what dpdx is, we're integrating here at constant x, so that is not a problem. So we integrate this first term here, which is the Poiseuille flow. So we can integrate that part to get the volumetric flow rate. That gives us the first term, which is 1 divided by 12 mu dpdx h x to the cubed. And this term here, the Quet flow, is going to give us a second term, which is minus 1/2 of uhx. So if you want, this here is the volumetric flow rate, which is due to the Quet flow, so which is due to the dragging of the flow from the top plate or from the bottom plate, depending on which frame of reference you're sitting in. And this here is the net volumetric flow rate due to the gradient of pressure in the x direction due to the squeezing of the film. So here, this now is going to be equal to, we're imposing the mass balance. So this term, which you see as a function of x, is actually going to be a constant. It's going to be equal to q0. And so we can inverse this relationship to express dpdx as a function of q0 and h. So that's what we do here. You can do that really quickly, and you find that q0 is equal to, so sorry, I'm writing it here. So q0 is equal to, this constant is equal to our expression, from which we can extract the pressure gradient. So dpdx now is going to be equal to minus 12 mu divided by h cubed times q0 plus 1/2 of uhx. And so we can separate the two terms again, one which is due to the quet flow, so 6 mu u divided by h squared minus 12 mu q0 divided by h cubed of x. So here we finally find the pressure distribution, or at least we find the pressure gradient. We know how the pressure varies as a function of x. So note that from this expression here, we know how the pressure gradient in the x direction depends on x. So now we know how it depends with the position x. But what we still don't know is q0. Right? Q0 here is still undetermined. And it is undetermined because we haven't said yet what our boundary conditions are for the pressure. So that's what we have to do next.